The next topic we're going to go into is work. Now, work is a term that's used in our everyday vernacular for about anything that seems like we exert ourselves, whether it's working in school or working hard, cleaning dishes, or whatever it is going on. But in physics, work is very specific. It's the amount of energy we expend, so it's all about energy, to displace an object by exerting a force. Note that we have to displace an object. The equation work equals force times displacement, where the force and the displacement must be parallel. So be careful of that. If there was an angle between the force and the displacement, we'd have to throw in this cosine theta, and we're not doing that just yet. Now, this idea that we expend energy to displace an object is very important. There must be a displacement. So if there's no displacement, S is 0, then you have done no work. You could push on the wall all day long with everything you have, and yet you would have no displacement, and so you would do no work. Likewise, if you had already lifted some books up to some height and you carried those books across the room, the force you were exerting on those books is vertical and the displacement is horizontal. So if the force you are exerting is upwards, try to keep those books from moving, and you are moving horizontally, the displacement and the force are perpendicular to each other, not parallel, and so there would be no work. Anytime in an equation you see two terms being multiplied, that probably means, if it's just like force times displacement or something else, let's say with impulse, force times time, that more than likely means we're going to deal with area under. If we have force on the y-axis and displacement on the x-axis, the area under that graph, that is the area measured down to the x-axis, or if we were down negative underneath, measured up to the x-axis. But the area under a force displacement graph is the work done. And be very, very careful here that it's displacement, because you could get impulse and work quickly mixed up. Impulse is force times time. It would be a force time graph, and the area underneath is the impulse or the change of momentum. Work deals with force and displacement, and the area underneath, right, force displacement graph is work. Right now I want to work a few simple example problems for us to where we can kind of get an idea how these problems go. We have some student walking down the hallway to class, and she does 375 joules of work to walk the 15 meters to the classroom. And the question is, how much force does the student actually exert walking? So solve for F. First thing I did is I drew a picture, and the reason that pictures are really crucial in almost every element of physics, and in this one in particular, pictures are very good here for work because we need to make sure that everything is perfectly aligned, parallel to each other. The force isn't going vertical and the displacement going horizontal. Otherwise, the total work would be 0. You'll see that here in a moment. We're doing 375 joules of work moving forward. She is applying a force to make her body move forward, and the displacement is going forward 15 meters per second, or excuse me, 15 meters. So now I rewrite my equation. I have created a variable bank inside of my picture. It could be a good thing to separate out a variable bank also if need be, but I created a variable bank by labeling my picture very, very well. So work is 375 joules. Joules is the base unit for work. I didn't mention that enough back in the first slide. Joules is the base unit for work, which oddly enough is also the base unit for energy. More to come on that later, capital J, 375 joules. And I'm solving for force, and I know my displacement. The girl walks 15 meters. Now it's just basic algebra. And so dividing both sides by 15, I come out with 25 newtons of force is needed for the girl to walk down the hallway. So she applies a constant 25 newtons of force, or an average of 25 newtons of force. Next question over here says, all right, let's use the exact same student, and now let's tack on a 19-kilogram book bag. So I sketch a quick picture of what's happening, and I know the girl is applying some force. We actually calculated the previous force, 25 newtons to go this way, and she's going to go a 15-meter distance towards the classroom this way, and here's her book bag. And the book bag has a mass of 19 kilograms. Now, note, mass is not the same thing as force. You'll see that coming up here, and you already know that, but we're going to apply that again somewhere else. But which direction is the force the girl has to apply to the bag to cause it not to fall? Well, it's upwards. Her shoulder has to apply a force of lift upwards. Now check this out. Does she actually cause a displacement in the same direction she's applying a force? She isn't lifting the bag up anymore, nor letting it move down. In fact, the bag is staying at the exact same level as she continues to walk forward. There is no extra force that she's having to apply on the bag. Notice here, force that she's having to use to keep the bag up is going vertical, while her displacement goes horizontal. Those are perpendicular to each other, not parallel. So the total work that she's going to do, or the total extra work that she is going to do, would be 0 joules extra, which means whether you're carrying a backpack or not, whether this girl is carrying a backpack or not, she's still only going to exert 25 newtons of force and exert 375 joules of work. Now that might feel very weird to you because whenever you are biologically, you are carrying something very heavy, you're like, hold on a second here. Just because I'm not lifting it or letting it go down doesn't mean that I'm not doing work. If I had to stand in the same place or walk around the room carrying a huge rock, it would feel like a lot of work that day. Expending energy biologically is not necessarily the same thing as spending energy for work in physics. Spending energy for work in physics must be, if you will, productive. You must create a displacement for whatever force you exert. In other words, if the force you are exerting does not create a displacement for that object in the same direction, you have done no work on it. Next question that I want to go into, we have our weightlifter over here, like you saw in the first slide, and we want to see how much work does the weightlifter do to lift 50 kilograms, 2 meters off the floor here, 25. First thing I need to realize is mass, my 50 kilograms, is not a force. So whenever I create my variable bank and I rewrite my equation, I start substituting in, that 50 kilograms does not go in for force. In fact, I have to figure out what force this is. And the force that a person has to exert to lift something up, if we're not trying to accelerate it up, we're just trying to lift it at a constant velocity, the force you have to use to lift, F lift, must perfectly balance out the force of gravity. So that might be something that it's something you've heard before in this class, but something worthy of writing down. To lift something up, assuming minimal amount of force, you're not trying to use extra, the force you have to lift something is equal to the force of gravity. So the force that we are going to lift with, I'll use FL times S, is the exact same, just opposite in direction, but is the exact same value as the force of gravity here. And I do know an equation for gravity. The force of gravity is mass times gravity, right? mgs. Now, this equation should look quite familiar to you. mg times some displacement up. In fact, think about what would happen if you replaced that with h. What would this, instead of work equals mg h, well, we didn't learn that in terms of work, but we did learn that in the previous video of gravitational potential energy. More to come on that later. Now it's just substituting in numbers. And so whenever I plug in numbers and I punch them into the calculator, I come out with sig figs, 2 sig figs here, it looks like, 980 joules. Something to remember from all of this. It's things you already know. Mass is not a force, so you cannot plug 50 kilograms in for the force. You actually have to figure out what that force is. And for you to lift something at constant velocity, that force to lift something at constant velocity is equal to the force of gravity. So minimal force that you need to use to lift something is equal to its weight or force of gravity. Force of gravity is mass times gravity. That allows you to substitute in and solve. Now, whenever you're trying to solve for work or something else, but the force that you're using is constantly changing, like maybe according to this graph here. So there isn't a constant force. Since there's no constant force, you cannot plug into W equals Fs, right? Because there is no single number to plug into the force. You would have to calculate the average force, and that could be somewhat unpleasant. You would have to weight each of these individual forces, and here the forces are constantly changing in a linear manner. So that equation doesn't work. Instead, what we need to realize graphically is area under a force displacement graph, or area down to the x-axis, is the work. So the first question, how much work is done in the first 4 meters, means, hey, let's take the first 4 meters right here, and let's figure out how much work is being done, aka what is the area under the graph. Now I see 2 definite shapes here that I could divide off. I see in a very light yellow a triangle in this area right here, and then a rectangle, let's maybe use blue, and then a rectangle right here in this area. And if I add up that area, then I get the work done. Now, area of the triangle, I'm dividing it into 2 pieces, right? Area of the triangle is 1/2 base times height. Area of the rectangle is base times height, and so that'll be my total work that I'm going to end up doing. Now, my triangle here has a base of 2, right, and a height of 3, getting the area of this piece, because if I add this piece to that piece, I get the total area under, which is the work done, for that entire section. So 2 times 3, 1/2, 2 times 3, 1/2 base times height, base of 2, height of 3. And then my rectangle has a base also of 2 and a height of 3 as well. Just be very careful here. What people end up using is they see what number is at the very end. And so they would say the rectangle has a base of 4. Well, that's not the case. The rectangle's base runs from 4 to 2, or 2 to 4, which is a base of 2. And I come out with the work done between over those 4 meters, according to the graph over here, is 9.0 joules, the area under 9.0 joules. And in the next problem, I actually want to solve what was the work done for all 11 meters. Well, I already know the work done here is 9 joules, so that just means I need this area over here. There are multiple shapes that I'm going to end up needing to cut out. In fact, looking at this, especially whenever you have some sort of height, check out some of the pieces that I might want to draw. I see a triangle here with a rectangle underneath it. I see another large triangle on that end, and then a large rectangle in the middle. And you could divide this up into any pieces that you would like. So I'm going to have a 1/2 base times height for this triangle here, a base times height for this rectangle, a base times height for the large rectangle, and a 1/2 base times height for this other large triangle on the other side. And then I need to add on these 2 pieces, which added up to be 9 joules. I try to color code our 4 areas here: base times height for this rectangle, 1/2 base times height for this triangle, base times height for that tall rectangle, and then 1/2 base times height for that tall triangle. Be very careful here. You can't call this entire area one triangle because you're missing a chunk of the triangle over here. This has to be a rectangle with another triangle on top of it. Now I get to substitute in all the bases for each one of these. Note that they're not all the same, right? And all the different heights for each of these, and add it all up. I do want to point out the height of this green triangle. It's starting out at the 3 spot and going up to 6. So the height, 6 minus 3, the height is 3 also. All right, so there's all the base times heights filled in. This would probably be a good point to say, pause the video and actually go back to this picture. Look at all the chunks, maybe rewind the video to see before I divided it all up into chunks, and maybe see if you could do it even before I divided this up at the very beginning of the slide, and see, hey, if I need to get the area under this entire thing, what pieces would I divide it up into, and then can I actually work it out into triangles, rectangles, and what would each base and height of those be. Then you can come back to this point. If you pause it, you could just hit play, and then see if what you're doing aligns with what I am doing. In some cases, you can actually find other ways that you can create different shapes in there, different triangles and rectangles. I'm not too sure if this is one of those cases, but actually go back and make sure you know what you're doing now. And I come out with 42 joules would be the total work done. The next question, what average force was exerted? So instead of trying to count up all of these thoughts, and trying to average out all these different forces here, the way you solve this problem is first, you do the area under to find the total work done. Now that you know the total work done, you are going to actually substitute in to force times displacement, to the work equation here. I know the total work, 42 joules. And now I'm able to solve for the average force as if we exerted the exact same force the entire time to move these 11 meters, getting up to using 42 joules of work instead of applying a little force at one point and more force at the other. And I come out with, it would have taken an average of 3.8 newtons of force, and we're right in here, right, 3.8 newtons of force, to do the exact same thing as what I did with changing how hard I was pushing with each passing meter.